Hello everyone, I'm Isaac Olson, and we're here from Group B12 along with Dimitri Akamaru, Kerry Chen, and Alan Kong. We're from EECS 203, Discrete Math, and we're going to be talking about relation operations today. So if you recall, relations are just a subset of the Cartesian product of two sets. So if you have a set A and a set B, a relation is just a subset of what we have here. So it could be just a mapping from elements in A to elements in B. It doesn't have to be one-to-one. It's not a function. It's not a It's a little bit more broad than a function. So since a relation is just a set, all of the simple set operations do apply to it. So you can use a union, you can use an intersection, difference, complement, and they all work exactly like a normal set. The only thing you need to remember is that a relation is an n-tuple, so you need to remember both elements of the n-tuple. So now there's a few other operations that only apply to relations and not to sets, and we're going to talk about those in a little more detail here. So composition is a specific way to merge two relations, and it's used to find, one of its uses is to find connectivity. So if you have three sets, I'm going to go to the next slide for this, and you have members of each set. So we have A and B. Let's make a relation between some elements of A and elements of B. So I'm just going to give them each three generic elements here. So let's say that this is our mapping of relations. So if you'll recall, this means that, call this R1. So this means that R1 is equal to A1 comma B2 A2 comma B1 and A3 B3. So now we want to do a composition. So say we have one more set C and another relation R2. So let's make another generic mapping here. And now our rule here is AC is in S composite R. I should have called these S and R. Let's do that here. R and S. AC is in SR as long as AB is in R and BC is in S. So what this is going to do is it's going to basically follow these lines and cut out the middleman. So now we're going to have S composite R is going to have elements of A and elements of C. So now A1 is going to be mapped to C3, A2 is going to go to C2, A3 is going to go to C1. So just like that, composition is pretty easy. You just basically follow these paths and you cut out the middleman. Now what this is used for in databases is linking two things together. And then when you want to know the relation between two things that are not necessarily in the same part of the database. So if you have one database that's a list of students and classes, and then another one's that's a list of classes and professors, but what you really want to know is what students have what professors. So we can write this kind of, we have one relation that is from the set of students, students to classes, and then we have another relation that is from classes to professors, and then if we compose these relations, we're going to get a relation that is going to be from students to professors. So you can see this is going to be useful in a lot of different ways when you're using with databases. A little more in-depth example here. So now we can actually apply a composite multiple times to itself, and then we're going to call this a power, which is another operation we're going to talk about. So R to the first power, R is a relation here. R to the first power is just R, so very simple, just like any other thing you're doing powers with integers. But however, R to the n plus 1 is just R to the n composite with R. So what this is going to do is it's going to, if you were to expand this whole thing, you're just going to have a whole lot of the composite operator applied repeatedly to itself. Now this is actually useful in graph theory because this is how you're going to find a transitive closure of a given graph. And so graphs can be used to represent relations, so it's also the transitive closure of the relation. So if you have a relation or a graph that has any number of elements, and say the graph is represented by the relation r, if you have r to the kth power represents the set of elements that are connected by paths of length k. So, and then obviously we can take this and raise it to the n power, and that's going to give us the transitive closure. So we're going to include every path that's distance or length 1, length 2, length 3, all the way up to the number of elements that are in a graph. And for one of the other videos on graph theory, they're going to talk about how all the number of the paths from two elements, the shortest path between two elements is no more than n. So we only have to include up to r to the nth power. And this actually can be used for a lot of different things in graph theory and database type applications. One of them would be, interestingly, determining the connectivity of computers of the internet. So internet could be represented as just a huge relation of between connections between different computers. And if you were to form this transitive closure, you can get all the connections between every computer. And so obviously there's almost like there's an uncountable, or not an uncountable, but there's a lot of connections, and this is obviously not nearly the number of connections that are in the US, but this is probably just main hubs. And this is just a kind of a diagram of the connection of main hubs around the world, and you can see that it actually kind of defines shapes of continents. But connectivity is obviously a very important thing when talking about this type of subject. Another operation we can apply to relations is the join operation. And this is just going to be used for merging two relations that share a couple of common elements. So if you have one relation that has n elements, or m degree, and then another one that's n, but say they share a certain number of elements. So you'll notice they both have these elements in them. And every single element, or every element of R is going to have some elements that are going to be common with another element of S. Because so remember that the R, each element of R has n, or m, it's an ordered m tuple. So we're going to take these, and we're going to merge these into this new relation here, which is going to be J of P, and P right here represents how many elements they share in common. So here's a quick example with it. Say one database includes students' names, students' ID numbers, and birthdays, and another one includes students' names in each class they're taking. So joining these relations across the field of student names, right, because they're sharing this part of their set, this will allow you to have a full relation that has the students' names, their ID numbers, their birthdays, and every class they're taking. Here's another quick example of it. Over here you'll see we have a relation of lecturers, courses, and the department that course belongs to. And then over here, we're going to have a relation of courses, department, room, and time. So you'll see that these two elements here are shared. And when we merge them with the join operator, we're going to merge across those two, and now we're linking together the lecturer. It's going to come down here, and the rooms and times are also going to be merged into this as well. So now you have a relation that represents the combined data that's represented in both these other ones, so it's a little more succinct. Final operation we're going to talk about today is the projection operation. And this function produces a relationship of smaller degree from a relationship that's larger. So say you have a relation that has a lot of fields in a database. So you have like, let's just for example say you have all of these fields. You have lecturer, department, room, and time. But maybe you really only want to know the room and time because you just need to know which rooms are available at what times. So you can then project this relation onto a relation that's going to be smaller. That's only going to have those two elements. So the way we notate this is we have a P, and then the subscripts here are just which the ith element that we're going to include, that we're going to include in that relation, in the new relation. So here's a little more detailed example. Here we have professors, metric number, a department, and these are students then. Their ID numbers and their department and their GPAs. But say we just want to know their name and their GPA. So we're going to project them on the elements 1 and 4. So that's going to delete these two columns, bring it down here, and now we have a much more succinct relation with the data that we want to know. and nothing more. So we're not transporting a huge structure around. So thanks for watching. Again, I want to recommend you to go to www.knoatom.com for more discrete math videos. And thanks for watching.